I have to tell you, I spent the last 3 days practically tearing my house apart.
Oh, no.
Yeah, there was this low-level hum in the kitchen, just this maddening constant frequency. I pulled the fridge out, checked the HVAC. I even put my ear to the floorboards thinking it was the neighbor's vacuum.
Please tell me you didn't start tearing into the drywall.
I came close. I really did. But strangely enough, that phantom noise is actually the perfect primer for today's deep dive.
Ugh.
Because we are looking at the ultimate background noise, the hum of the universe itself.
And unlike your kitchen, scientists are actually using this hum to solve the biggest feud in astrophysics right now.
Right, the Hubble tension. For those of you who track this, you know the drill. You measure the early universe via the cosmic microwave background. You get an expansion rate of about 67.
Right.
But then you measure the late universe using stars and supernovae, you get 73. They don't match, and everyone is basically yelling at each other.
Exactly. And the problem is both sides have incredibly robust data, which is where this new research from the University of Illinois Urbana-Champaign and the University of Chicago comes in. They've developed a method called stochastic sirens.
Stochastic Sirens. I love the name. It sounds like a Greek myth meets a heavy metal band.
It really does. But functionally, it's a major pivot from how we usually use gravitational waves. Usually we hunt for standard sirens.
The really loud ones.
Right, those massive singular black hole crashes. It's like standing in a quiet room and hearing one person shout. You can pinpoint exactly where they are and how far away they are.
Okay.
But stochastic sirens don't care about the individual shouters. They look at the stochastic gravitational wave background.
So to use the analogy, if a standard siren is a soloist, this background is like the roar of a crowd at a stadium.
That is the perfect analogy. You can't distinguish a single conversation in that stadium roar, but the volume and the pitch of the collective crowd tell you a huge amount about how many people are there and what they're doing. Yeah, this hum is caused by countless unresolved black hole mergers happening across cosmic history, all just overlapping into a single background signal.
And here's where the methodology gets really clever. We aren't looking at stars or dust or standard candles. We are bypassing that whole electromagnetic distance ladder that causes so many arguments. This is just pure gravity.
Precisely. It's an independent ruler. But here is the nuance that I think makes this study so elegant. We haven't actually definitively detected this hum yet.
Which, usually in science, no detection sounds like a failure.
It does, but in this case, the silence is the data point. Current data from our detectors, LIGO, Virgo, and KAGRA, shows that the gravitational wave background is very quiet. That silence is incredibly constraining.
Because if the universe were expanding slowly, fitting that lower Hubble constant of 67, the background shouldn't be this quiet, right?
Exactly. The expansion rate determines the volume of the universe at different times in history, which influences how often black holes merge and how those signals pile up. If the slow expansion models were correct, they predict a higher density of audible mergers. Essentially, the background hum should be louder than what we are currently hearing.
So the silence is effectively ruling out the slow universe scenarios. It's too quiet for the expansion rate to be 67.
Right. Even without a positive detection of the hum, the upper limits of the noise level are already pushing the probability toward the higher numbers, toward that 73 range. It's bridging the gap just by elimination.
That is such a cool, rigorous flip, measuring the universe by what you don't hear. It's all about finding the signal in the noise, or in this case, the lack thereof, which honestly is the hardest part of any complex system.
Is this your segue to Embersilk?
You know it is. Speaking of complex systems, this deep dive is sponsored by Embersilk. Look, if you need help with AI training or automation or integration or software development, Embersilk is the partner you need.
Absolutely.
They are experts at uncovering where agents could make the most impact for your business or your personal life. Check out embersilk.com for AI needs.
It's a great parallel, actually, because in cosmology, that separation of signal and noise is about to get much better.
And that's the really optimistic part of this study. They aren't saying, we found nothing, let's go home. They have a real timeline.
They do. Experts anticipate a definitive detection of this background hum within the next 6 years.
6 years? That's incredible.
It is. As the detectors get more sensitive, we're going to move from it's too quiet for the slow model to here's the exact measurement of the fast model. It really highlights human ingenuity.
It's a total game changer. It means we finally have a third independent way to measure cosmic evolution that doesn't rely on light at all. It makes me so hopeful about our ability to decode the universe.
It's the dawn of gravitational cosmology. We're moving from just seeing the universe to listening to its collective history. It's a structurally unique way to test our standard models.
It really makes you wonder what else is out there just waiting for us to turn on the right microphone.
Exactly. It suggests that the answers to our biggest questions aren't always in the bright flashes we can see. Sometimes they are in the quiet collective history of everything happening in the background. We just have to build the tools to listen.
A beautiful, inspiring thought to wrap up on. If you enjoyed the deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.